I'm sure you all are doing well and moving on with this particular MMPC 005 unit of yours. And we are into our unit 5, block 2. And today we will be covering basic concepts of probability. So let us first of all understand what exactly it is. Really, the uncertainty in our real life problems. This builds or this brings into the need for our probability. Suppose say the rainfall and the climate conditions which are very unpredictable, and those things impacts on our agriculture, irrigation and disaster management. This is one sort of real life situation. One more, maybe your stock market issues like prices that are fluctuating due to your dynamic factors, due to which the investors investing in the stock market will be facing uncertainty in the returns that they will be getting on their investments. Similarly, one more situation maybe the variability in production leads to defects, so the quality outcomes are also not always certain. So these are certain uncertainty problems that basically arise in our real life situations when we are functioning. So the poor reality is the future outcomes are very uncertain and cannot be predicted with certainty. So, because of which our decision making becomes complex and risky. Hence, the managers sometimes face certain challenges like how to make decision under this uncertainty and how to estimate risk and possible outcomes. So perhaps the solution path to overcome these sort of uncertainty problems is convert uncertainty into measurable likelihood by using the data and structured analysis. Here comes our probability. That means the probability provides a scientific and qualitative framework which helps in assigning likelihoods to uncertain events. This makes or this enables our informed, rational, and data driven decisions. That means we may say over here or we may conclude over here that probability is perhaps the bridge between uncertainty and decision making. So, what exactly, or how can we say, or how can we define our probability? It is basically the measure likelihood of an event to occur. We can't say that certainly it is happening. So, what is the percentage of probability of happening that particular event? So, probability is the measure of the likelihood of an event to occur. So in case of events, we basically can't predict with total uncertainty. We can only predict, suppose say the cancer of an event to occur. That is how likely it is to happen. We can't say when it will happen, how long it will stay, when it will go, but only we can say how likely it is to happen. So probability basically it ranges between two numbers, one is 0 and one is 1. That means 0 indicates that the event, or you may say happening of that particular event is impossible. Indicates that event to be an impossible one, and 1 indicates that it certainly happens. For example, suppose say you are having a coin, you want to toss the coin, there are only two possibilities, either your head will appear or tail will appear. But if we toss two coins, then there may be three possible outcomes. That is, maybe both the coins will, on both the coins head will appear, or on both the coins tail will appear, or one will head and one will tail. So, what may be the complementary? In case of such events, there will be only two outcomes. That is, when an event will occur or not occur. The complement of an event occurring is an exact opposite, that the probability of an event is not occurring. It may or may not rain today. Or suppose I have purchased a lottery ticket, I may would win the lottery or I will lose the lottery. So there are only two happenings. One is happening and one is not happening. So one is opposite to the other. So both these events are complementary events. So basically the terminologies that we use while discussing or while measuring the probability number one is sample space. Whenever we are making certain experiment, the set of all possible outcomes that occur in any tree. For example, if I'll be tossing a coin, then my sample space is there will be only two and only two outcomes. One is head and one is tail. So my sample space is head and H and T, only two. Similarly, if I'll be rolling a dice, which are having six faces 1, 2, 3, 4, 5, and 6. So my sample space is the set of all the six numbers. But it is one of the possible outcome which can occur, that is called as a sample point. That means all the outcomes, that all possible outcomes is sample space, and one of the outcome that happens is a sample point. So in a deck of cards, if I'll be drawing cards, say four, out of those four, three hearts are to appear, the three is the sample point. So experiment or trial, that is a series of actions where outcomes are always uncertain. Means I will be conducting or I will be performing certain trials, but at the end of each trial, what will be the outcome? That is not certain. That is very uncertain. That is called as an experiment, or in other words, we may say it as random experiment or a trial. So example, maybe tossing a coin, choosing a card from deck of cards, or throwing a dice. And event, one more term is event, that is single outcome of an experiment. So whenever I am tossing a coin, getting tail is an event. Similarly, outcome, possible result of an experiment. So head is a possible outcome when a coin is tossed. Impossible event means the event that can't happen. That means suppose I'll be tossing a coin. If it is impossible to get either head or the tail at the same time, it is very impossible to get head and tail at the same time. We can get either head or tail. We can't get both the outcomes at the same time. That is an impossible event, which can never happen. Then, in the context of probability, an experiment is any occurrence that can be observed. For example, rolling a pair of dice and finding the sum of the numbers is an experiment. Suppose say I'll be throwing two dice simultaneously. An outcome is one possible result of the experiment. For example, in that rolling of the pair of dice, I will be finding one outcome, that is the sum of both the dice rolled dice. The sum of the numbers is 7 and the second outcome is 11. Okay, the outcome. So every experiment has one or more outcomes. The sample space S of an experiment is a set of all possible outcomes. For the experiment of rolling a pair of dice and finding the sum of two numbers on the dice, the sample space is, say, S is equal to 2, the sum of the two numbers on the dice. Maybe it may be 2, or it may be 3, or maybe 4, like this. So here, if I'll be rolling both the dice simultaneously, I may get 2, I may get 3, 4, 5, how many ways I can get this often. So The sample space is all the possible outcomes. That is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Often there may be one or more outcomes that you are particularly interested in. For example, we are interested in the sum of numbers on the dice being greater than 5. That means what is the probability that I will be, when I am rolling two dice simultaneously, the sum of the two numbers on the dice being greater than 5. The event, suppose say it is E, would be the subset of the total sample space. Our total sample space is to this one. Okay. So if that event is E, that I will be getting that the sum of the numbers on the dice being greater than 5 is a subset. E would be the subset of the total sample space. That includes all the outcomes that we are interested in. That is, all those for which the sum is greater than 5. That outcome is called as your favorable outcomes. Okay. So if E is the sum of the numbers on the dice being greater than 5, then E is equal to the set of the numbers which are all greater than 5. That is 6, 7, 8, 9, 10, 11, and 12. So there are many possible events that could be considered for any given experiment. So this is what is an example that we have taken. So consider the experiment of a rolling of a pair of dice again and finding the sum of the numbers on the dice. Let E event with the sum of the two numbers which is greater than 5, then E will be equal to the set of all the numbers which are greater than 5, that is 6, 7, 8, 9, 10, and 11. And suppose say one more event, that is F, be the sum of the two numbers which is even, that is 2, 4, 6, 8, 10, 12. Okay, we are having these two numbers. One is the sum of the two numbers is more than 5, and another is the sum of the two numbers is even. These are the two events, say E and F. So we can have the event operations. One operation is complement of an event. That means the event that includes all outcomes in the sample space which are not in event. That means in that we have taken E as the event in which you may say the pair of dice we have rolled, the number appeared is more than 5. So this E complement says that it will be containing all those numbers which are not more than 5. That means all which are less than 5. So 2, 3, 4, 5. This is the complement of that E, not in E. Okay. Similarly, union of events. That means if we are having two events E and F, E is all the numbers greater than 5 and F is all my even numbers. Okay, so the E union F of events, meaning union of two events, includes all the outcomes of either E or F. That means the outcome, if it is appearing in E and or else in F. If it is appearing in E, then also it will be there in E union F. And if it is in F, then also it will be there in F. That means it is a combination of both E and F. Just that means 2, 4, 5, 2, 3, 4, 5 plus 6, 7, 8, 9, 10, 11, 12. Both. Okay. Similarly, intersection means the common elements. Okay, that means which is there in E as well as in F. Not E or F, but E and F. In that case, we may say it will be 6, 8, 10, 12. Okay. This is E. So E union F is 2, 4, 6, 7, 8, 9, 10, 11, 12. Okay. So with this, we should add 2, 4. That will be E union F. And E intersection F means we are having common elements of these two. That is 6, 8, 10, and 12. Okay, 6, 8, 10, 12. So if the events have the same theoretical probability of happening, then they are called equally likely events. That means whenever you will be throwing or you are tossing a coin, either head will appear, may tail will appear. Whichever, everything, the possibility is equal. So those two are called as your, that means result of sample space are said to be equally likely if all of them have the same probability of occurring. Suppose say some examples like getting 2 or 3 while we are throwing a dice, or getting 1, 3, 4 whether we are throwing a die, or whether getting a head or a tail when we are tossing a coin, all are equally likely since the probability of each event are equal. Okay. So we can represent that E union F or E intersection F by using Venn diagram. By Venn diagram, I mean each of the event is presented by using a circle to help visualize the way different events or sets, each of the set we represent by using circles and the sample space by using a rectangle or a square. To help visualize the way different events or combinations of events interact with sample space, we consider this Venn diagram. This diagram has a big rectangle which represents my sample space. Okay, that sample space is all the possible outcomes that I can get when I perform a random experiment. So within us, all possible outcomes through 12 appear in various spaces. The circle labeled E represents the event E. The sum of the numbers is greater than 5. That is 6, 7, 8, 9, 10, 11, and 12. Okay, whereas similarly the circle labeled as F, this represents the sum of all the numbers which are even, that is 2, 4, 6, 8, 10, and 12. So this place where both the circles overlap and only the outcomes that are both in event E and F, that is 6, 8, 10, and 12. So this is basically in set theory we represent the union and the intersection. Okay. So experimental outcomes, suppose say, consider one experiment, that is, suppose say 3 coins I am tossing simultaneously, recording the sequence of heads and tails. Okay, A be the event that there are exactly 2 heads, and B the event there are exactly 2 tails. Now, if I'll be tossing 3 coins simultaneously, then the outcome will be this 8. Okay, and typically when working with an experiment, suppose say, we will be finding out certain things like say H commonly represents the getting heads and T getting tails. Okay, so suppose say one is find the sample space for the experiment, list the outcomes of event A, that means all exactly 2 heads, and outcomes in event B, that is there are exactly 2 tails, and create a diagram that shows the sample space events A and B and all of the outcomes. Okay, so here is the solution that I have made for you. Now find the sample space of the experiment. Over here I am throwing 3 dice, 3 coins, so my outcomes will be maybe all will be head, maybe 2 heads, 1 tail, and so on. So I will be having all 8 possible outcomes. So the sample space is the all possible 8 outcomes out of the 3 coins tossing simultaneously. Then list the outcomes in the event, that means at least 2 heads, that is maybe HHT, HTH, 1, 2, THH, these are the 3. Okay, out of 6, out of 8, I'll be getting 3 times 2 heads. Similarly, 3 times 2 tails, and create a diagram which shows the sample space events A and B and all of the outcomes. So the total sample space In A, I'll be having two heads at least. In B, I'll be having two tails at least. And barring these two, I'll be having two more outcomes. One is all tails and all heads. So this is my total sample space, and this is my A set, and this is my set B. And over here, by looking at the diagram, I can pretty well say that there are no outcomes that are both in A and B. Okay, that means circles never overlap. So the events, we say the events in probability, each random experiment consists of a set of elementary events forming a sample space with n elements. If I am having, since each subset of the sample space represents a possible events, the total number of possible events is 2 to the power n. Okay, I have tossed 3 coins. 3 possible outcomes are 2, one is head and one is tail. So the total possible outcomes is 2 to the power n, that is 2 to the power 3, that is equal to 8. So these events can be classified based on the nature of occurrence. So some events always happen, we call them as certain events, while others, they never happen, we call them as impossible events. And some involve multiple outcomes, we call them as compound events. And while others are either mutually exclusive or exhaustive. So we will be discussing with examples what all this is. Understanding this qualification helps us to analyze probabilities efficiently and apply them in our real world scenarios. The certain events, an event that always occurs whenever an experiment is performed, is called a certain event. In other words, an event associated with a random experiment is called a certain event if it is always occurs whenever the experiment is performed. So consider the experiment of rolling a dice, which are having 6. At least one of the event is the event of getting an even or odd number is a certain event. Either you will be getting 1 or a 2 or a 3 or a 4 or a 5 or a 6. So you will be getting either an odd number or an even number. Certainly you will be getting that. So getting an odd number or even number, that event is a certain event. And in the certain event case, we say the sample space is this and event is maybe 1, maybe 2, maybe 3, maybe 4, maybe 5, maybe 6. So in this case, in case of certain event, your sample space is equal to the set of event, the event. So thus, if an event includes all possible outcomes in the sample space, then it is called as a certain event. Okay. Next is impossible event. An event that never occurs whenever an experiment is performed is called an impossible event. In other words, an event associated with an experiment, random experiment, is called an impossible event if it never occurs whenever the experiment is performed. For example, if I'll be rolling a die and if I'll say the event of getting a number divisible by 7, which is an impossible event as because possible outcomes are 1, 2, 3, 4, 5, 6 only, and none of it is divisible by 7. So whenever I'll be rolling a die, I will be getting either 1 or 2 or 3 or 5 or 4 or 5 or 6. So if I'll say what is the probability or what will be the outcome of getting a number divisible by 7, then my event will be containing no value or no number. So it is no element will be there in B, which is divisible by 7. So it is an impossible event. Thus, if an impossible event contains no possible outcomes in the sample space, it is an impossible event. And we represent that by using 5. Then compound event, if one event, whenever you are performing an experiment, an event with more than one outcome is called as a compound event. These events occur when 2 or more elementary events are grouped. In other words, an event associated with a random experiment, compound event, if it is the disjoint union of 2 or more elementary events. So consider rolling a die. The event of getting an even number is compound event because it consists of multiple outcomes. My even number may be 2, maybe 4, maybe 6. So my outcome may be 2 or 4 or 6. So when I roll a die, getting an even number is a compound event as because it is having multiple outcomes. Mutually exclusive, two or more events are mutually exclusive if the occurrence of one event prevents the occurrence of the other. This means that both the events have no common outcomes. So whenever I roll a die, getting an even number, possible outcome of getting an even number, never having an outcome of getting an odd number. So, in other words, two or more events associated with a random experiment are said to be mutually exclusive events if the occurrence of any one of them prevents the occurrence of all others. That is, if no two or more of them can occur simultaneously in the same trial. So when I consider rolling a die, let A is equal to 2, 4, 6, that is getting an even number and getting an odd number. So if I'll be taking an intersection or A intersection B, then there are no common outcomes. So if A intersection B is equal to 5, then we say that the event A and the event B are mutually exclusive. That means occurrence of one event prevents the occurrence, never prevents the occurrence of another. Then exhaustive events. So two or more events associated with the random experiments are exhaustive if their union is the sample space. So events, suppose say A1, A2 and so on AN associated with a random experiment, and A1 union A2, union A3 and so on, union AN is equal to S. So in other words, a set of events is exhaustive if the union covers the entire sample space. This means that at least one of the events must occur in every experiment. Okay, if A1 is one event, whatever be the possible outcome, A2 is another event, the possible outcomes, A3 is another event, possible outcomes, and if I'll be making a union of all those events, then at the end I'll be getting the entire sample space as the union of the events. If that is the case, then I'll say the events are exhaustive events. So suppose say we are having a deck of cards, that is, you know that we are having 52 in a deck of cards. So A is getting a red card, suppose a B is getting a black card. So A union B is equal to the entire deck, that is the sample space. So these events, that means A and B are exhaustive. Okay. Similarly, when I'll be rolling a die, getting an even number is suppose say A1, getting an odd number is suppose say A2. Then possible outcomes of A1 are 2, 4, 6. Possible outcomes of A2 are 1, 3, 5. So if I'll be making a union of A1 and A2, that will be 1, 2, 3, 4, 5, 6. That is the sample space of all the possible outcomes if I'll be rolling a die. So hence I may say that A1 and A2 are exhaustive events. So mutually exclusive and exhaustive. So a set of events are mutually exclusive and exhaustive if each event is disjoint, that is mutually exclusive, and their union covers the entire sample space. So in this case, again, rolling a die, getting uneven numbers, 2, 4, 6, A1, and event A2 is getting the odd numbers, 1, 3, 5. So A1 and A2, A1 union A2 is equal to S, and over here again, A1 intersection A2 is 5. That is disjoint. So these two events are mutually exclusive and exhaustive if their union is sample space and intersection is an impossible if they are disjoint. Okay. So again, if a deck of cards, one more example, A1 is a card of spades, A2 is the event of getting card as a club, it is a heart and a diamond. Since every card belongs to exactly one suit, So all suits together means A1, union A2, union A3, union A4 is the all possible outcomes, that is the entire deck, that is my sample space. And the events are mutually exclusive as because A1 intersection A2 is 5 and so on. Everything is disjoint. So all are mutually exclusive and exhaustive. So favorable and elementary events, if an event A consists of a certain desired outcomes, then the outcomes that contribute to the occurrence of A are called favorable elementary events. That means consider rolling a die. Suppose say event A is getting a multiple of 3. So possible favorable outcomes of getting multiples of 3, that is A is equal to 3 and 6. So thus outcomes 3 and 6 are favorable elementary events for event A. Okay. So similarly, in rolling two dice, if A is equal to getting the sum of 8, then my favorable outcomes will be if I'll be getting 2 and 6 as 6 and 2 or 4 and 4, 3, 5 and 5, 3. Thus the favorable elementary events when I throw two dice simultaneously, then getting the sum of 8 possible favorable elementary events are 2, 6, 6, 2, 4, 4, 3, 5, and 5, 3. Right? Then, next is the what are the different approaches to probability theory. Basically, there are three different approaches to probability that have evolved, mainly to cater to the three different types of situations under which probability measures are normally sought. One is classical probability. Of course, I have described over here the four, but written over there three. Classical probability, relative frequency, or it is called as your empirical approach. One more is subjective probability approach, and one more is your axiomatic approach of probability. So let us now explore each one. To start with, the classical approach, how we define it, it is applicable when all outcomes are equally likely while throwing a die to get a head or a tail that is equally likely. So over here, probability is defined as, suppose say a event A, probability of the event A is equal to number of favorable outcomes by total number of outcomes. So basic idea over here is every outcome over here has equal chance of occurrence. So based on logical reasoning, not the data, we have this classical approach. So for example, we may say drawing a number, suppose I am having 9 numbers, 1 to 9. So I am drawing a number, so getting the number 4. So total outcomes are 9. The favorable outcome is 1, that is 4. Okay, getting the number 4 is the favorable outcome. So the probability of getting A is equal to 1 by 9. Okay, the number of, over here we said number of favorable outcomes is 1. The total number of outcomes is 9. So 1 upon 9 is the probability of getting number as 4. So each number over here has equal probability. If that is the case, then only your classical approach applies. So what is it exactly? Example, experiment, throw a die. Getting an even number, sample space is this. Even numbers are 2, 4, 6, that is we are having 3 outcomes. The probability of getting an even number when we throw a die is 3 outcomes. Total favorable outcomes are 3 divided by total outcomes, it is 6. So my probability is 1 upon 2 or half. Similarly, in case of cards, drawing a card from a deck, we are having, suppose say getting an ace, we are having 52 cards, that is total sample space is 52. The favorable aces outcomes are 4, that means we are having 4 ace in my deck. So the probability of getting an S is 4 by 52, that is 1 by 30. So, when can we use this classical approach? If outcomes must be equally likely, then only we can apply classical approach. Sample space must be finite and known, and it is basically suitable for games like dice, cards, coins, and theoretical models. It is not suitable when outcomes are not equally likely and the sample space is not clearly defined. The advantages, it is simple and easy to apply and it doesn't require the past data for its application. Whereas the limitation, it assumes, that is, it works on the assumption that all the events that are occurring are equally likely, then only, and it is not always realistic. It is not applicable in real world on certain situations. So what can be? It is used for risk modeling in controlled environments, decision making in structured scenarios, and classical probability provides a logical starting point to understand uncertainty. Okay. The next is our relative frequency approach. It is probability is based on past data or observations. If the long run relative frequency of an event, it is the long run relative frequency of an event. So over here, probability of an event is number of times that event occurs divided by the total number of trials. The core idea is your probability over here is estimated from experience of the data. More trials, more accurate probability. That means over here, as you increase the number of trials, your accuracy level of measuring the probability will be enhanced. So suppose say I'll be tossing a coin for 100 times and I observed that 52 times head has appeared and 48 times tail has appeared. So what is the probability of getting a head over this? That is 52 times divided by the total number of experiments that I have conducted is 0.52. So exactly, we always say it is not exactly 0.5, it is based on actual observations. Similarly, suppose say I have administered a drug on 200 patients and outcome is that 150 patients had a positive impact of that particular drug, then probability of recovery 150 have recovered. So 150 and total patients that I have administered is 200. So 150 by 200 is 0.75. So it is basically used in healthcare and public health decisions. And rainfall, suppose say past 20 years data of rainfall records, 8 years had heavy rainfall. So what is the probability of getting heavy rain? So 8 divided by 20, that is 0.4. This sort of thing, again, it helps in agriculture planning and water resource management. So when outcomes are not equally likely, we may use relative frequency or this empirical approach. It is based on the number of trials. More the number of trials you can perform, the better will be the results. So when historical data is available, this is more suitable. So it is suitable for your business forecasting, quality control, market analysis, basing on the previous year's market performance. Advantages, it is realistic and practical based on actual evidence, but the limitation is it requires heavy data as because we have to perform number of trials. As the number of trials grow, the accuracy grows, so it is time consuming. The past may not always predict future, that may not be authentic also. So it is used in demand forecasting, risk analysis, investment decisions. So it is data driven probability. It transforms your experience into actionable insights. So subjective probability next is based on your personal judgment, belief, or expert opinion. It is used when past data is limited or outcomes cannot be measured objectively. It reflects how likely a person thinks an event is to occur. It depends on experience, intuition, available information. So you may say, as because it depends on experience, intuition. So different people may assign different probabilities to the same event. So it is common in business, finance, policy, and strategic decisions. Suppose a new product launch, a company plans to launch a new product. Marketing manager believes there is a 70% chance of success. So probability of success is 0.70. This estimate is based on market understanding, consumer trends, and the managerial experience of your marketing manager. Similarly, suppose a solar power plant, I want to commission a solar power plant. So experts estimate 60% probability that it will be a successful venture. The probability of success is 0.60. Again, it is based on exact historical data which is unavailable. So decision must still be made. So stock market situation, maybe an investor feels a stock has a high chance of rising next month based on news, trends, and intuition. She assigns probability of price rise in that particular stock is 0.65. This is not exact measurement, but informed judgment, as because it is based on certain intuition, news, and trends. So the characteristics of subjective probability is based on belief or opinion, useful when data is very rare or scarce, influenced by knowledge and expertise, and it is definitely vary from person to person. Then axiomatic approach or to probability is developed by a statistician or may say mathematician Kolmogorov. It provides formal mathematics foundation of probability, and over here the probability is defined using a set of basic rules called as axioms. Core idea over here is that probability is not based on outcomes or data alone, but it should satisfy certain universal principles. So there are basically three axioms. Number one is non-negativity, that is probability of any event is always non-negative or positive. It is always greater than or equal to zero. And axiom 2 is that total probability is equal to 1. That is probability of the sample space is sucked. That is a we said no all the events A1 union A2 union A3 and so on is equal to 1. That is probability of sample space is equal to 1. Total probability is 1. Each of the possible outcomes, if the probability of each of the possible outcome, if you will add on, then it will be 1. Then axiom 3 is probability of A union B. If A and B are mutually exclusive, then probability A union B is equal to probability A plus probability B. Probability either A or B is equal to sum of their probabilities. That is the axiom 3. It is additive if both the events are mutually exclusive. So throw a die, event A getting an even number, it is 2, 4, 6. The probability A is equal to 3 by 6 is 1 by 2. It satisfies probability is positive. Total probability is equal to 1. That is all the events is 6 by 6. Similarly, cards getting an ace 4 by 52, getting a king 4 by 52. If A and B are added, then probability A B is equal to, that is it is a ace as well as a king. As because both these events are mutually exclusive, so A union B is 4 by 52 by 4 by plus 4 by 52. It is 8 by 52. So it provides universal framework. It is applicable to all types of probability, and this removes ambiguity and assumptions, and it works for your classical, empirical, and subjective approach of probability. So key advantages: it is logical and consistent, and it is applicable for all complex problems. It forms the basis of modern probability theory. So managerial insights, maybe it is It supports in or it helps in risk modeling, decision analysis, financial modeling, and operations research. So axiomatic probability provides the foundation on which all your probability models are built. So this speaks about the various approaches of our probability theory. So far we have made the probability that basing on a certain event to happen. Now we will be using it in decision making in real life. So how your probability affects the decision making in real life. The role of probability in decision making. Your probability helps in making informed decisions. Basically, decision making is a continuous process in both personal as well as garment seller. He estimates demand using probability, finds high probability in of large cells, so decides to stock large quantity. But what happened? What actually happened at the end of the season? He find that a unsold stock remains. Initial probability estimates turn out to be inaccurate. This indicates. So this requires a revision. So new experience provides that additional information. Earlier probability must be updated. That means earlier he said that estimated that sorry, demand using probability was very high of large cells. So because of which he made a large stock, and as a result of which at the end of the season he found a huge amount of unsold stock remained. So this indicates that his probability calculation measure is not proper, so it needs updated. So future decisions should improve using this learning. So key insight. In real life, probabilities are not static, they are continuously revised as new data arrives. So arrival point over here comes one more concept called as your Bayes theorem. It provides a formal method to update probabilities. It incorporates a new evidence into prior beliefs, leads to better dynamic decision making. So Bayesian thinking transforms your experience into smarter future decisions. Okay. So Bayes theorem, it is a method to update probability using new information. It combines prior belief, that is initial probability, and the new evidence. It helps revise decisions when new data arrives. Okay, really, basically, your Bayes theorem is a mathematical formula used to determine the conditional probability of an event based on prior knowledge and new evidence. Okay, basing on a specific event that has already occurred, but we have to perform another event. So, assuming that an event has already occurred, it is there. We have to take a decision on the basis of that this is already there. On the basis of this condition, we have to take the decision that how can this likelihood. Okay, it adjusts probabilities when new information comes in and helps better decisions in certain uncertain situations. Okay, so probability of A given C, okay, is probability of C with that this A has already happened, and probability of A divided by probability of C. Over here, P, probability of event A, that is prior probability, it has already happened. Probability of happening the event A. Okay, then probability of C, given that A has already happened, that is likelihood. And A has happened, but C is to happen. That is posterior. It has already happened. It need to be happened. Given this condition, this has to happen. That is updated probability. And C is total probability of event C. Further to explain, basic terms related to this theorem are hypothesis. This refers to the possible events of outcomes in the sample space. They are denoted as A1, A2, and so on, AN. Each hypothesis represents a distinct scenario that could explain an observed event. Okay, priori probability or probability that AI has already happened is the initial probability of an event occurring before any new data is taken into account. That means previous year this has already happened. In this year this will happen given the new data. Okay, any new data, before any new data is taken into account, what is the probability of the event? That is your priori probability. It reflects the existing knowledge or assumptions about the event. For example, probability of a person having a disease before taking a test is a priori probability. Then posterior probability is the updated probability of an event. That is, this probability of the disease is already there. Considering the new information, that is the probability of having a disease given a, that means after assuming that this disease is already there, they will be performing certain other tests. Basing on the tests, the decision will again be taken. That is the posterior probability. Okay. Then conditional probability, the probability of an event A based on the occurrence of another event B is the term conditional probability. It denotes as probability A bar B and represents the probability of A when the event B has already happened. B has already happened, what will be the probability of A with the B happened? That is the conditional probability. And joint probability, when the probability of two or more events occurring together and at the same time is measured. It is marked as joint probability. Suppose say we have two events A and B. It is denoted by joint probability is denoted as A intersection B. Probability A intersection B. Okay. Random variables, real valued variables whose possible values are determined by random experiments are called as real valued variables whose possible values are determined by your random experiment are called as your random variable. And the probability of finding such variables is the experimental probability. Suppose say we are having a manufacturing case, probability of A is equal to 0.6 with correct setup. Probability of the event B is equal to 0.4 with incorrect setup. Okay. And the defective rates given, that is probability of C given that the setup is correct is 0.1 and probability of C that the setup is incorrect is 0.6. Sure. The C is that product is defective. Product is defective with correct setup is 0.1. Product is defective with incorrect setup, the probability is 0.6. So total probability is equal to probability of C given A into probability A plus probability of C given B and probability of B. Okay, so it is 0.1 into 0.6 plus 0.6 into 0.4, that is equal to 0.30 total probability. Then apply the Bayes theorem. It is given C or conditional probability of happening A given the event C has already happened is 0.1 into 0.6 by 0.30. Sorry. So it is equal to 0.2. How can we interpret that? The initial belief is that our probability of happening the event A is 0.6. After defects are observed, probability of A given C is 0.2. So confidence in correct setup drops sharply. Okay. So new information changes earlier belief. Initial belief is that probability of A is 0.6, and with after defects are observed, so we have said the probability of A given C is 0.2. That means when we have observed the further information, whether we have updated the probability with the correct setup, the probability of getting the defects has come down sharply. That is what the new information defect changes earlier belief. So extended example maybe new probabilities. C given A is 0.01. Probability of C given B is 0.36. So if we will be applying our Bayes theorem, then the probability of A given C is 0.04. So your Bayes theorem helps in updating decisions with new data, and it is basically helpful in risk analysis and forecasting, quality control, and in the present day, it is very much useful, used, or you may say extensively used in your artificial intelligence and machine learnings. So better decisions come after updating beliefs with evidence. So if we will be updating our results with the present day information, then definitely the decisions will vary. So your Bayes theorem helps update probabilities using new information. It combines prior belief plus new evidence. So the calculation of the probability or measuring the probability will be a revised probability. And the key formula over here is probability of an event with condition that C has already happened is equal to probability C given A into probability A divided by probability C. So in Bayesian thinking flow, your prior is initial belief, that is probability of the event A. Evidence, new information is that the event C. The likelihood is that the probability of C given A. And the posterior, that means updated belief, is that after the C has happened, what will be the probability of A? That is my posterior. Okay, prior belief is before getting the new information or new evidence C. That is prior probability, and posterior is after the likelihood of C given A. The posterior will be A given C. So key probabilities, and from this we can conclude that probabilities are not fixed. They change dynamically, and they change dynamically with the new data. So managerial relevance of this Bayes theorem is decision making under certainty, risk analysis and forecasting, quality control and diagnostic, AI, finance, and business strategy. So your Bayes theorem transforms uncertainty into learning and better decisions. So Bayes theorem proves that if you will be updating your measure of probability with the information that is coming or that is updated, then your decisions will be better definitely. So what are the formulae that we have covered so far are the three axioms, that is our probability of A is from 0 to 1 and sample space is 1 and probability of impossible event is 0. And complementary is if it is not event A, then it is a complementary event. Addition rule, probability of A union B is probability of A, probability of B minus probability A intersection B, and if both A and B are exclusive mutually, then it is probability A union B is A plus probability A plus probability B. And multiplication rule is general case, probability A intersection B is probability A is into probability B given A, and independent events, if both A and B are independent, then probability A intersection B is equal to probability A into B. And conditional probability, probability A with the condition that B has already happened is equal to probability A intersection B by probability B. So we have discussed that a random experiment is a process or activity whose outcome cannot be predicted with certainty. So even though all possible outcomes are known, a random experiment, when we are conducting, the outcome is not predicted. So, and we have covered Bayes theorem and the total probability theorem. That is, probability B is equal to probability B given A1, probability A1, and so on. So where A1, A2, and all these are mutually exclusive and mutually exhaustive. Exhaustive events. Mutually exclusive means the union is sample space, and exhaustive means they are disjoint. That means probability A intersection B is equal to 5 in null set. The classical probability A, probability of the event A is equal to favorable by total, that is equally likely outcomes, and relative frequency is probability of the event is equal to number of occurrences by number of trials, and subjective probability and axioms are three that we have covered. So probability is equal to tools for decision making under uncertainty. With this, we conclude. So thank you. I have these things whenever it is required. So definitely you will be capturing all the audience attention. Thank you.